first I'd like to say thanks to Ross, Mike and Al for including me on this panel of distinguished EV experts. You've heard from Quinton a great overview of LED technology and some of the fundamentals of the science. I'm going to take a slightly different tack on this and draw from some historical precedents of technologies that have come into existing marketplaces and led to change, and use that as a basis to paint a picture of where we think at EXFO the LED technology is going. So a few words about EXFO. We're basically a solution provider. And that's a bit cliche, but we provide our solutions through high-quality instrumentation and through a detailed understanding of our customers' processes, bringing those two things together to create a high-value proposition for our customers. We're a moderate-sized company of about $180 million US last year, growth-focused. We're headquartered in Canada, with corporate offices in Quebec City, and the division that I'm with, the Life Science and Industrial Division, located in Toronto. Worldwide representation, and we're publicly traded, so if you're interested in some more background, you can find us on the NASDAQ and also on the Toronto Stock Exchange. Within EXFO, there is Excelerate. And Excelerate is a business line that was started about 5 years ago to develop specifically UV solutions for digital drop-on-demand applications. And of course, inkjet printing is one of those target applications that we're looking at. This represents a multi-million-dollar investment by EXFO, and it includes our investment in an on-site material research laboratory. And the intent of this laboratory is not to develop new materials. It's actually to study the interaction of our light sources with the existing material systems that our partners are utilizing, in order for us to customize the light source and design it so that we have the most efficient curing possible, and to optimize the configuration of the light source. Currently, our product line includes both traditional arc lamp type sources and LED sources. So, enough of the preamble. What's our perspective on LEDs? Well, we see LEDs as disruptive technology to this industry. And when I say disruptive, I'm talking about the definition of disruptive that's common in innovation literature that exists today, in which the technology enters into a marketplace that already has an incumbent technology, but this new technology has certain basic properties associated with it. It's simpler than the incumbent technology. It's more convenient to use. Generally, it's smaller, and it's less expensive. LEDs either are, or we believe soon will, have all of these attributes. But, and here's the caveat, but it really depends on your perspective and from which market segment you're looking at this technology choice. One easy way or convenient way of trying to illustrate this graphically is to plot as a function of time some parameter that's very important in the market space that we're studying. For this illustration, I've chosen the wide format graphics. We could also have chosen narrow format label. It's another area that LEDs are emerging. And on that chart, you take a look at what's the minimum expectation of the marketplace on that parameter space, and what's the upper range. And this really defines a band of expectation, a band of requirements for the technology. We chart on that same graph the evolution of the incumbent technology, which right now is arc lamps. And arc lamps essentially satisfy the full range of applications within this market space. And they're evolving as that market space evolves. On this same chart, I plotted the progress or change that's taking place right now with LED technologies. And this is also another important distinguishing attribute of disruptive technologies. The pace of change of the disruptive technologies is far in excess of the pace of change of the incumbent technologies. Where are we right now? Well, we believe we're right here, on the cusp. And we can debate that. I mean, you'll hear all of the panel speakers talk to the applications that are more suitable or less suitable at this point today for LEDs. But what I really want to focus on is the trend, the slope of this graph. Okay? Why do we think the that graph has such a steep slope? Well, we've been in LEDs for about 15 years. EXFO has been producing UV light sources for about 25. And back in 1999, we launched our first UV LED system to the marketplace. We were the first actually to produce a UV curing system. And this was targeted at adhesive curing. So back then, when we put that system out, our ability to gather the light from the LEDs and direct it down onto the work site where it was needed was quite low, only about 10%. And that has to do with the Lambertian nature of the emitters and the crude nature of the optics that were available at that time for utilizing the light from the LEDs. Flash forward now to today, collecting and directing almost 50 or over 50% of that radiation to where it's needed. Active areas, you heard earlier that active areas have changed. 10 years ago, we could only get 100 by 100 micron LED dye. Today, we can get dye that are greater than a millimeter by a millimeter squared. That's quite significant because it has significant impact on the system design and architecture of the system, and it also allows us to use very standard optical techniques to collect and direct that light as we need it onto the substrates. Irradiances have increased from 10 watts, from 1 watt per centimeter squared in that early prototype that we put out, to over 10 watts per centimeter squared today. In the ink curing space, this is huge because we know that there's a certain energy density necessary. You have to exceed that energy density in order to get curing to take place and complete. Now, cost. When we put that system together 10 years ago, the cost of the dye, just the dye alone, not any of the other peripheral hardware associated with creating the system, just the dye alone costs us $160 per watt of UV light generation. Today, that number is down to $6 per watt. What's driving all of this change? Well, over the past 10 years, it's really been the general lighting industry and the push to move to LED-type sources for general lighting. We think that that technology push for general lighting will continue to influence the evolution of UV LEDs as well. LEDs represent only one part of the equation, and referring back to that graph that I showed you about the evolution, the parameter that I showed is really curing. So LED curing involves obviously the LED, but it depends on the material systems that we're trying to cure as well. And there's been significant progress over the last 3 or 4 years on creating specific inks, so inks that are specifically cured by LEDs. Now, this is even newer as a field of study than the LED work that you're going to hear about this afternoon. But within the past 3 or 4 years, there's been tremendous progress made. And in particular, the energy dose requirements for LED-specific inks have dropped by somewhere between a factor of 3 to 6 times for integrated dose required to cure that ink. As well, the spectral response requirements of those inks have been tailored to the extent possible so far with the research that's been done to make it overlap more effectively with the monochromatic nature of the LED sources. So a lot of work has been done. I'm not saying that all the work is complete on LED specific inks. As a matter of fact, I think there's a lot of room left for us to move forward with inks, particularly when we think about the fact that there are so many different applications where we wanted to use digital inks for printing. Where are we today?